First of all, thanks for the opportunity to speak here. Let me just quickly introduce myself. So I'm Ranjit Deshmukh. I'm from the University of California, Berkeley, as well as I work at the International Energy Studies Group at the Lawrence Berkeley National Lab. And today I'm going to present on the cost and value of wind and solar in the Indian electricity system, focusing on the 2030 year. And my co-authors, I want to acknowledge Dr. Duncan Callaway, Nikita Bhankar, and Amol Farke. Great. So the way I've structured this presentation is I'll give a bit of context and then a little bit of the methodology and then spend more time on the results. So the context is solar PV and wind, both costs are reducing drastically. That's why we all know this. But solar and wind are variable in time. As you can see here, this is just diurnal variation where the wind is varying as well as solar is coming up and down during the day. But there's also interannual variations as well as seasonal variations. Solar and wind also vary in space. Especially for India, most of the wind and solar resources are concentrated in the west and the southern states. And then they're uncertain, which means we have forecast errors. As we get closer to actual dispatch, these errors reduce, but day ahead, we still have errors, and that may introduce more cost to the system. And because of these attributes of wind and solar, we just cannot look at the levelized cost of energy. It's just inadequate to assess the value of wind and solar to the overall system. So before I ask the questions for the study, I just want to be clear of some terminology. There are three different components in this study that we are looking at. One is the cost of VRE. VRE is variable renewable energy, and that's the term I'm going to use for both wind and solar. So the cost, as we estimated, is the levelized cost of energy, which just includes capital cost, operations and maintenance costs, and then it depends on the resource quality of wind and solar. The second component is the capacity value of VRE. And this is the avoided capital investments in new conventional generators compared to like a no RE scenario. The third component is the energy value of VRE. This is the avoided variable fuel and operation and maintenance costs of conventional generators. Okay, so on one side we have the costs, the levelized cost of energy, and then on the other side we are looking at the value where VRE is avoiding investments in conventional generation and operations of conventional generators. Okay. So the two questions that we are asking in the study, the first one is, how does the mix of wind and solar affect the energy and capacity value of variable renewable energy? And the second is, what is the additional long-run benefit or cost of VRE to India's electricity system at different penetration levels, as in different targets for renewable energy, and different mixes of wind and solar? Okay. These questions we are applying to the Indian national grid in the year 2030. And we are looking at three different capacity targets: 200 gigawatts, 300 gigawatts, and 400 gigawatts. And then we are looking at 5 different capacity mixes for wind and solar. And they vary from 0 to 100%, 25, 75, 50, 50, 75, 25, and 100, 0. So for example, for 200 gigawatts, we are looking at 0 gigawatts of solar, 100 gigawatts of wind, or 25 gigs of solar, 75 of wind, and so on. And for each of these scenarios, we are comparing the system cost of VRE compared to the no VRE scenarios, as in 0 wind and 0 solar. So let me run quickly through the methodology, and I'm not going to ask you to read all of this little text, and I'll apologize for the font. But there are basically 3 components again. The first one, here we are looking at the VRE build-out costs. Here we do the geospatial site suitability analysis where we use wind data from Vaisala and solar data from NREL. And we exclude some certain land use land cover categories, certain elevation and slopes that are not suitable for wind and solar development, and protected areas. Once we have the areas where we could potentially put wind and solar, we then select our renewable energy sites to meet each of the targets for wind and solar in each of our scenarios. Okay? And I'll go a little bit in detail in the next slide. And then we create the generation profiles for wind and solar for each of these scenarios, which is the hourly generation, like megawatt generation level across a whole year. In the second component, we estimate the new conventional capacity build-out cost. So here we use the forecast for 2030 using the recently released 19th Electric Power Survey forecast for India. And we use the 2014 load as our annual generation load for India, and use those Electric Power Survey forecast numbers and create load profiles for 2030. We then use a simple graphical screening curves approach that I'll show on one of the slides to create the new additional conventional capacity that would be needed to meet peak demand. In the last part of this methodology, we use a unit commitment and economic dispatch model to determine the system operations costs for different scenarios. So here's the maps for the VRE build-out, where on the left you will see the wind suitable areas, and on the right is the solar PV suitable areas. We are only looking at solar photovoltaics. And here we have just shaded different targets like 100 gigawatts, 200, 300, 400 gigawatts for each of wind and solar. We have established one constraint for this. We are not allowing each state to cross more than 15% of the overall target, because we didn't want all the sites to be selected in just one area, which sort of mimics how different states pursue renewable energy here in India. But all these sites are selected based on the highest capacity factors. We are not optimizing based on their profile and their value to the overall system. Once we select those sites, then we come up with the costs. So here, across the entire potential of wind and solar, we estimated the variable renewable energy costs using different capital cost assumptions. And we benchmarked those levelized cost of energy estimates against the recently achieved solar, the wind auction price, and then the solar PV auction price. So you sort of adjusted our capital cost based on that. One thing I would like to point out is the blue line, which is the wind cost, varies much more across India than solar PV. So which means as you increase your wind targets, the cost increases because you will be developing wind on lower resource quality sites. In reality, would we see those increase in costs? Perhaps, maybe not, because we're also seeing higher hub heights and bigger rotor diameters. But we haven't included those effects in this particular model. Next, in the conventional capacity build-out model, this is the screening curves. For those of you who haven't used this approach, I'll quickly run through this. In the top graph, on the x-axis, you will see the hours for the whole year, so 0 to 8760. And on the y-axis, it's the net load, so in gigawatts. The 2030 load forecast is the red line on top, which is the load duration curve. And then for each of these scenarios, we subtracted the wind and solar, which is must-run generation, from the load. And then we also subtracted the must-run generation like run-of-river hydro, minimum generation hydro levels for storage hydro, as well as nuclear. Once we got that, we then used hydro energy budgets for 2014, and we spread them across, so we have monthly energy budgets that we spread them across every day. And for each 24 hours, we dispatched hydro to again reduce that net load curve. So this is sort of a net load for India. So each of these lines are for each of these scenarios. Then on the bottom side, you will see we used only 3 technologies as conventional technologies that India could potentially invest in. One is coal. The second is CCGT, but using LNG prices, so pretty expensive, liquefied natural gas. And then CTs, which are combustion turbines or peaker turbines, also operating on LNG. And these particular lines, where they intersect is the fixed cost for that technology, and then the slope is the variable cost. It's a very typical approach for capacity expansion models, where these lines intersect. You just graphically extend them onto to your net load, and then the difference between these points are the capacity of each of the conventional generation technologies that you want to invest in. Okay. The last part of it was the systems operations one. Again, I apologize for many equations here, but I just put it on the slide so researchers can access that later. But just quickly, what we are doing is we are minimizing the overall system cost. So this model is optimized over 24 hours. And then we keep on optimizing it for 365 days. So the objective function is minimizing cost. The first constraint is just supply equal to demand, right? The second is that generation has to be lower than rated capacity for each generator, right? Straightforward. Then the generation for each unit has to be higher than the minimum generation level for that unit. And this is not imposed for combustion turbines, which are peaker turbines. So which means we are not allowing any coal unit to shut down and start up within those 24 hours. So that's a constraint that we use. So it's a conservative assumption. And then we use muster generation has to meet that same generation levels. The VRE generation, we allow it to be curtailed, and that's why you see this less than sign here. And then finally, it has to meet the hydro daily energy budget. So hydro is being dispatched over those 24 hours. Okay, so I want to spend more time on the results. Enough of the boring part. So the first result is the capacity build-out scenario. So as you can see on the x-axis, we have all these different scenarios. The first one is the no RE scenario. And then for each of these 5 scenarios, all the results that I'm showing go from 0% solar to 100% wind, and then goes all the way to 100% solar and 0% wind for the 5th scenario. And this is the 200 gigawatt target, the 400, and the 200, 300, and 400 gigawatt targets. What we saw in this particular exercise was that the avoided conventional generation capacity per megawatt of wind or solar installed is really low in India. And that's because of the weather patterns in India. India has a evening peaking system. So obviously, solar has almost 0 capacity credit, even after we dispatch the hydro, because hydro is going to be a small percentage of the overall capacity in 2030. And wind has really low capacity factors for about 7 to 10% of the hours. And that's why, if you look at these numbers, we are only seeing about 0.03 or 0.09 megawatts of conventional capacity being avoided by VRE megawatts. So really low capacity credit. Okay, then through the systems operations model, this is the VRE curtailment that we saw in each of our scenarios. Again, just to remind you, so one thing I forgot to mention was we do not consider transmission constraints in this particular model at this point. There's also uncertainties associated with transmission in 2030. So we just want to get insights on how the cost evolves for different shares and penetration of wind and solar. Okay, so for the wind curtailment, for the VRE curtailment, we are seeing 2 different insights. So VRE curtailment increases with greater RE capacity, which is intuitive. But we're also seeing more curtailment with greater solar share. So you can see the right-hand side, all these shares have much more solar than wind. This is 100% solar. So for the 400 gigawatts, we are seeing really high curtailment levels of more than 30%. Again, we are not assuming any storage or DR on this system. At the high penetration, VRE curtailment is lowest for 25% solar and 75% wind. So it is all these number 2 scenarios for each of the penetration levels. So VRE in total generation. This is the share of VRE. Because India sets its policies based on capacity targets, we did not do this analysis based on energy targets. These are only capacity targets. So as the capacity increases, obviously the share increases. But as solar increases, the share of VRE is lower because solar has lower capacity factors. Okay, because of curtailment of solar, the blue lines are even lower. So as you can see, the share of VRE will be lower once you have more curtailment. Okay, now this is the energy and capacity value. We have combined them together. Okay, Again, to remind you, the capacity value is the avoided cost of investments in new conventional generators, and then the energy value is the cost that we are saving in terms of energy and operations cost of conventional generation. So here you can see this particular chart. Now it can be shown in two ways. It's either per megawatt hour of VRE after curtailment, or we could have shown it before curtailment. So here we are showing it after curtailment. For the 200 gigawatt scenarios, you can see, for all these scenarios, you can see the capacity value is quite small across these scenarios. But they're highest for the 25% solar and 75% wind shares. For the energy value is not changing much across all the scenarios. If you would change this, the denominator to before curtailment, then it would be dropping much more. But that cost is reflected in our cost of VRE. Okay, so number one, both energy and capacity value are greatest for 25 and 75% of solar wind mixes for all targets. The second is energy value is similar across all VRE mixes and build out. And this is because of the dominance of low cost and very similar cost of coal units, okay? And the third one is capacity value is low across all scenarios. It's an evening peak, as I mentioned before, as well as low wind CFs for almost 7 to 10% of hours. Okay, then we used this capacity value and energy value and then subtracted the cost of VRE, okay? Or essentially the other way around. So we subtracted the value from the cost. So this is the VRE additional cost, and the denominator is per load because we wanted the same denominator across all scenarios. Okay, so this is the load for 2030. Here you can see how the additional cost changes. Again, it is lowest for 25% solar and 75% wind. The cost is fairly small. I mean, it's relative, but we don't want to get stuck on this cost because we haven't included the additional cost for ancillary services as well as transmission. But what we saw was about 0.06 to 0.16 INR per kilowatt hour for 200 gigs, and then about 0.25 to 0.56 INR for 400 gigs. I'm almost out of time. I'm just going to get a few seconds. We did a few sensitivity analysis on how this trend changes. So the first one we saw, okay, what happens when we change the 55% wind gen level to 70%? Intuitively, we are going to see more curtailment of solar. And that's why, so this is the base scenario, and then the right one is the sensitivity. So you can see how the cost increases for all these solar, heavy solar scenarios. Then we reduce the solar cost by 20%. What that does is our optimal is now changing more towards the solar heavy scenarios. But it happens more for the 200 gigawatts, less so for the higher ones because of solar curtailment, okay? When we reduce the wind cost by 20%, we see this opposite effect, of course. So wind scenarios are much more attractive. And then finally, if you reduce the cost of both wind and solar by 20%, which is realistic, for the 200 gigs one, we are already seeing some negative cost, which is like a benefit to the overall system. So I think these kind of simulations help us to understand the overall value of and cost of wind and solar. Quickly, the limitations of studies are, again, no transmission constraints because we have a lot of uncertainty. We haven't included uncertainty or forecast errors, which could be added to this particular model. Storage and demand response can definitely reduce the curtailment, especially diurnal storage and DR. And finally, we are planning to include more years of data because this is a time series data. We haven't used stochastics. And load shape changes would also affect the value of wind and solar. So for example, if we have more air conditioning loads in India, it could be a day afternoon peaking systems, which will increase the value of solar. Finally, my last messages are mix of wind and solar do affect the overall cost and value of VRE. India's evening peaking system, VRE is likely to have low capacity value. The high share of solar, especially at high penetration of VRE, leads to high curtailment, but DR and storage can help. And then finally, simulation exercises such as these would help policymakers to better understand the benefits and costs of VRE. Thank you.